Here is a puzzle that stumped computers for decades. To a machine, a word is just a symbol, a string of characters with no built-in meaning. So how do you make a computer understand that cat and dog are related, while cat and typewriter are not? The old answer was clumsy and hopeless at it. The modern answer, word embeddings, is one of the most elegant ideas in all of natural language processing, and it is the whole reason neural networks can work with language at all. It turns words into coordinates in a space where geometry itself carries meaning. Let's see how it works. At its heart, an embedding is built from one beautifully simple principle. Watch how a bare word becomes a point in meaningful space one step at a time. Start with a word as a raw, discrete symbol. On its own, it is just an entry in a vocabulary, an opaque token the computer cannot compare to anything. Nothing about the characters C, A, T tells a machine that a cat is anything like a dog. We have to give it meaning from somewhere. So we lean on a famous principle: you shall know a word by the company it keeps. We look at all the contexts a word appears in across a huge corpus, the words that surround it again and again. Cat shows up near purr, fur, and pet. So does kitten. That overlapping company is the raw material for meaning. From those contexts, the model learns to place the word as a dense vector, a list of maybe 300 numbers rather than a lone symbol. Words that kept similar company end up with similar numbers, so their vectors point in nearly the same direction. Meaning is now baked into a compact string of coordinates. Finally, every word lands somewhere in one shared space, and something remarkable falls out. Similar words sit close together, and relationships become directions you can do arithmetic on. Take the vector for king, subtract man, add woman, and you land right next to queen. Geometry itself is now carrying meaning. So what exactly did this replace? The contrast with the old approach is stark. Every word used to get a giant, sparse vector called a one-hot encoding, all zeros except a single one marking its slot. With 50,000 words, you get 50,000 dimensions, almost entirely empty, and worst of all, no sense of similarity. Cat and dog sit exactly as far apart as cat and typewriter. Word embeddings flip all of that. Each word becomes a dense vector, just a few hundred numbers, and crucially the distances between them mean something. Words with similar meanings sit close together, so the space encodes relationships you can actually compute with. Learning something about dog now transfers to puppy, because they live in the same neighborhood. Strip it down, and three ideas define word embeddings. They are dense vectors where distance reflects meaning. Instead of a sparse slot per word, each word is a few hundred coordinates, and closeness in that space encodes similarity, while directions encode relationships like the classic king, man, woman, queen analogy. They are learned entirely from data, from the company each word keeps. Methods like word2vec, glove, and fast text scan enormous corpora and push words that share contexts towards similar vectors. So meaning emerges from usage rather than being hand-coded by anyone. And a classic embedding is static, which is its key limitation. Each word gets exactly one fixed vector no matter the sentence, so bank by a river and bank with money collapse into a single blended point. That is precisely the gap contextual models like BERT later closed. Alright, let's lock in the essentials. Word embeddings are dense vector representations of words, positioned in a space where words with similar meaning sit close together and relationships become directions. They replaced the old one-hot encoding, where every word was a huge, sparse vector with no notion of similarity, cat as unrelated to dog as it was to a typewriter. They are learned from data by the principle that a word is known by the company it keeps, using methods like word2vec, glove, and fast text. Their main limit is that a classic embedding is static, one vector per word, which contextual models later fixed. If turning language into geometry fascinates you, There is a whole shelf of these explainers waiting at standarity.com. See you there.